So the topic we are covering today is the divergence, and if we have time, I'm going to look at the curl of the electric field E. Okay, and these two are mathematically very interesting, and physically it has a lot of application as well. Okay, and I guess you are already familiar with the general concept of the divergence of E. That's exactly the Gauss law, the very famous Gauss law that we use a lot in electrostatics. And in fact in other fields of physics as well. The idea is that the electric field E, which is a vector field, has a couple of very interesting and important properties, okay? And those important properties are manifested mostly in the divergence and curl of E. Okay, so what I'm going to do today, I'm going to start from a point charge and first look at the electric field created by a point charge, okay? And that can be generalized into any possible charge distribution, because any possible charge distribution, you can imagine that that's created by combination of many different point charges, okay? So first I'm going to look at that, and I'm going to look at the divergence of electric field created by a point charge. And next I'm going to look at that in more general way, and what I want to do is that I want to look at the electric field created by a continuous charge distribution and take the divergence of that and see what kind of properties I get out of that. At the end, I'm going to show that the divergence of electric field at any point in space is proportional to the charge density at that point. Okay, so that's going to be the conclusion of the topic I'm doing today. For the curl, the interesting property is that no matter how the electric field is created and no matter what charge distribution, regardless of the strength of the field and everything, the curl of the electric field always becomes zero. Okay? And that, in fact, becomes a basis that in the future chapter we can, not in the future chapter, future sections, we can define electric potential from that. And electric potential is interesting in the sense that electric potential is a scalar field. And from that scalar field, we can always calculate electric field. Okay? And that's mathematically interesting because the scalar field has one parameter and vector field has three parameters. Okay? So in a way, we are summarizing the information of a three-dimensional vector field in a one-dimensional scalar field. Okay? So, okay, if you let me keep talking, I'm going to talk too much. Let's get things started here. Okay? And then we will talk about potential later on. So we had this equation. So let me write a topic. Divergence and curl of electric field. Okay. And if you remember on Tuesday, we said that for any continuous charge distribution, we can write electric field at any position R in space as a function of the integral of 4 pi epsilon 0 integral of dq over r square times r hat, and that's it. Okay, so technically this integral gives us electric field at any point from any random possible charge distribution. dq, if we have volume charge density, it can be rho, the charge density, times the tau infinitesimal volume. If we have surface charge density, it can be sigma, surface charge density times dA infinitesimal area. For the line linear charge density, the dq is lambda, the linear charge density, times dl, the infinitesimal mass. Okay, so the equation as it is here is pretty general. Okay, and I can tell you the single most important question in electrostatics is in fact calculating electric field. Okay, so if hypothetically calculating this electric field was easy, we were done with electrostatics. Okay, the thing is that only for special cases we can do this integral. Okay, a lot of time it's so complicated that we cannot do it. A lot of time we do it numerically, but we cannot do that analytically. So it totally depends on the shape of charge distribution and amount of charge distribution. Okay, so because this integral is most of the time difficult, we come up with different methods to be able to calculate the electric field. Okay, so this is going to be like the perspective of what we're going to do, in fact, for the rest of this chapter and also chapter 3. Okay, so by the way, numerically one can more or less easily calculate this. Okay, so you can do the integral numerically, you can look at all these dq's in a space and then calculate it if it's electrostatic. So sometimes it's going to be time consuming. Okay, you know, people do a lot of simulation for atomic structure and interaction of like biological molecules. What they do is in fact integrating similar integrals, right, and then look at all these pairwise interaction and calculate electric field. But that itself can be very, very complicated depending on the situation. If you have too many particles, right, if you have too many particles, this integral is not easy to do it numerically either. Okay, so let's now go back and look at one single point charge. Okay, now imagine we have one single point charge, charge Q, okay, and let's demonstrate what sort of electric field we have around this point charge. Okay, we said electric field due to a point charge is ER 1 over 4 pi epsilon 0 Q, the charge over R squared distance times R hat, and that is the direction of the radial unit vector in spherical coordinates. Okay, so if you have point charge at any point, the direction of the field lines are straight going away from this point charge, something like this, and if it's positive, it's going away. If it's negative, it's going to converge to the origin. Okay, so something like this is what we get for one single point charge. Okay, now I want to look at one integral here, and that's the integral of the electric flux, phi E, which is the flux of the electric field. Okay, I want to look at this, and that's technically E dot dA, depending on what surface we choose. Okay, so this is an integral that goes on a surface. We have this field, and we can look at the flux on any surface, any random surface. As long as we have the electric field, as long as we define the surface, we can calculate the flux. Okay, so technically I can choose a random piece of surface here. Okay, I know where the surface is, I know the electric field. At any point at the surface, I can calculate this flux. Okay, so but what I'm interested in is flux on a closed surface which encloses this point charge. Okay, and the easiest way to do that, the most straightforward way, is looking at a sphere, something like this, that encapsulates the origin where the point charge sits. Okay, so that's the first thing I want to do. I want to look at the flux of the electric field passing through the surface of the sphere. Okay, and radius, you will see, does not matter here. Okay, so let's look at that. I'm going to use a spherical coordinate because I have spherical symmetry here. Okay, so for the electric field, this is exactly the equation I want to use. For dA, okay, I want to use this integral. I want to look at the dA in a spherical coordinate, and this is the small surface area, infinitesimal surface area on the surface of the sphere. So if you wish, we can show it like this. Okay, so this area is technically my dA. Okay, it's a small area on the surface of the sphere. Does anyone remember what was the equation for this? If you think about this, you can sort of create what you wanted. So this is a small change in the direction of theta hat and a small change in the direction of phi hat. The radius remains constant. Let me increase my volume. I'm not hearing it. Or no one was talking. Okay, let me write it here.
Is
So
it like r theta? Is that it? S equals r theta, or no?
so the A equals, let's write it down. You have a couple of components. One of them is r d theta. The other ones are sine theta d theta. So r sine theta d phi. Okay. So the lenses we have here, one of them is r d phi. Okay. So this is one side of this. No, let me fix it. It's r d theta, one side, and the other side of this square is r sine theta d phi. Okay, so this is the area. dA is a vector. What is the direction of this? For dA, the direction should be perpendicular to the surface. And if you remember, we said the convention is that if you have closed surface, dA points towards outward. Okay, and that means it should be in the same direction of r hat. Sounds good? Okay, things like this dA, we're gonna use that a lot. Okay, so you better have a good picture of how we can write dA for like a spherical coordinate if you are integrating on a surface. Okay, and the idea is that r d theta is this side. Okay, so this side is r d theta, and this side is r sine theta d phi. Cool. So this integral, if you put things together, it's going to be very straightforward. I'm going to do it here. The integral, because it's on a closed surface, I'm going to show it like this. This is our notation for any integration on a closed surface. I'm going to write S so that you see it's integral on a surface. EdA is going to be, so 1 over 4 pi epsilon 0. I can take it out of integral because it's constant, the same with Q. So Q over 4 pi epsilon 0. The integral is going to have 1 over r squared times r hat dot, here we have two r components, and that is r2 sine theta d theta d phi times r hat. Okay, so what we have here is a dot product, okay, both in the direction of r hat. So the dot product of r hat by r hat is just 1. So the integral is simply a two-dimensional integral, 1 over 4 pi epsilon 0. One of them is over theta, the other one is over phi. So this is, first write the one on theta. So r hat by r hat is 1. Also 1 over r squared cancels out with this r. We only have sine theta d theta, and then we have integral of d phi. Theta runs from 0 to pi, and d phi runs from 0 to 2 pi. Okay. So from one of them you get 2, from the other one you get 2 pi. Combine, you get 4 pi from these two integrals, and that simplifies with 4 pi in the denominator. Here we get 1 over epsilon 0 times q. Okay. So we did this integral, we calculate the electric flux, phi e, over the surface of the sphere, and it turned out to be 1 over epsilon 0 q. Okay. So there's something interesting about it, and that is the answer is independent of the radius of the sphere. Okay. So no matter how big this sphere is, small or large or super large, the flux that passes through the surface is 1 over epsilon 0 q, independent of the radius. But it depends on the charge sitting in the center, and that's proportional to q. Okay. Now, so it's independent of r, is it also independent of the shape? I chose a sphere here.
Yes.
What if I chose something totally different shape? Let's say random shape like this. Do you think the integral will depend on the shape?
No.
It will not. Okay, so the geometrical way of looking at this is you can look at one small angle here, okay? And then you can imagine whatever flux is passing through this one is going to pass through this surface as well. This surface here can have an angle relative to the surface of the sphere, but the point is that if it has angle, the area, the magnitude of the area increases very similar way that angle is changing. So at the end, if we calculate the flux passing through this surface of the sphere or passing through the surface of the random shape here, we get the same flux. Okay, so I'm going to generalize this to the fact that any surface, if we look at the flux integral of E dot dA, as long as it's a closed surface, this integral is 1 over epsilon 0 over q. Okay, and now since I said any random surface, that means random surface doesn't need to be like have a center at here. It can be anything as long as it encapsulates the charge q. We will have this integral equal to 1 over epsilon 0 q. Okay, so technically I can have a, let me use my blue marker. I can choose a surface like this, which is not like a sphere at all. Even on this blue sphere, okay, sorry, even on this blue surface, if I integrate the flux of the electric field, I'm going to calculate 1 over epsilon 0 times q. Okay, and that is interesting, right? From 2 points of views. One, from the fact that this integral, based on the divergence theorem, can be related to the divergence of E. Okay, that's one thing. The second thing is that we have superposition principle, meaning that if within one surface we have more than one electric charge, if we do this integral, we're going to have a combination of charges on the other side. Okay, and to show that mathematically, let's imagine we have n electric charges within that surface. Okay, so let me clean this up and draw another picture to make it easier to follow the discussion. Okay, so now let's assume we have this random shape. Okay, and let's imagine we have number of different point charges in it. Okay, let's assume we have n point charges, each of them with the charge of qi. Okay, now what I want to say is that at any point we have, let's say we have an electric field, and I'm going to call that electric field total because that's electric field created by all these point charges. Okay, so E total is a combination of electric field at any point in the space. I'm going to say that E total at point R. Okay. If we follow the superposition principle, this E total is in fact E1 at position R, which is the electric field created by charge number 1 plus electric field created by charge number 2, and so on. And I can write it in terms of a sigma I from 1 to n ei at position R. Okay, so this is technically how we can write the electric field created by all these charges. Okay, now if we have these, now let's look at the flux of the electric field. E total. Yes.
What does n represent?
N is total number of electric charges, point charges we have within the surface.
And is it q sub I or is it just q?
This is q sub I. Okay, so let's imagine these charges are different in terms of magnitude, and let's assume we have q1, q2, q3, all the way to qn. Okay, so what we have inside is like this: q1, Q2, Q3, all the way to Qn. These are charges that we have within the surface. We could have other charges outside, but you know what? It's very interesting. Who cares about that? What we care about at the end is charges inside that inside that surface. Okay, so phi total is the integral of E total dot dA. Okay, and since we can write E total in terms of that combination, the whole integral here can be written in terms of the sigma I from 1 to n, the integral on the surface of EI dA. Okay, so this is integral of the electric field due to one point charge within the surface, this integral. And then we just sum over all the possible charges that we have inside that sphere, okay? So we already calculated this, and we know that this is equal to 1 over epsilon 0 Qi. Okay, so this total flux is going to be equal to 1 over epsilon 0 sigma I from 1 to n times Qi. Okay, and if you look at this summation, what is this? Sum over all the charges from 1 to n, and that is technically the total charge enclosed within that surface. Okay, so and another notation for this is that we call it the enclosed charge Q enc. Okay, so that is 1 over epsilon 0 Q enclosed. Okay, so if we have any random possible charge distribution confined within that surface, if we look at the total flux on the surface, that's going to be equal to 1 over epsilon Q enclosed, the total charges inside. And it's interesting that this is independent of the geometrical distribution of the charges. It only depends on total charges, the magnitude of the total charges within this. And you can imagine if you have 1,000 electric charge within that surface, if half of them are positive, half of them are negative in a way that the total charge is 0, if you integrate the flux, it's going to be 0 because the total enclosed charge is 0. It doesn't mean that electric field at any point is 0. We will have non-zero electric field at all points, but if we integrate electric field and calculate the flux, it adds up to 0. Okay. And now the beauty of this is that in certain cases that we have certain symmetries, we can easily calculate electric field because from the symmetry we can come up with certain assumption of how electric field is distributed, and we can have assumption on what direction of the electric field should be, and that makes a lot of calculations easy. By the way, this as a whole is a famous Gauss law. Okay, integral of the electric field on the surface, which is the flux of the electric field, is proportional to the total electric charges within the surface. Okay. So far, so good. Any question?
Yeah, I have a question. I want to make sure
Sure.
that I understand what's
Of
going on.
course.
So the total flux is just the sum of all Q's divided by epsilon naught.
Yes, the total flux is sum of all Q's divided by epsilon naught, which is Q enclosed by epsilon naught.
Okay,
Cool.
thank you.
So, I want to do one expansion as well, two more expansion of the same thing, and that illuminates how we can use continuous charge distributions. Okay. So for that, I'm going to clean up here a little bit. So I think I can get rid of this. And all these ones as well. And I guess I can get rid of these things. So, and what I want to do now is that I want to go back to the divergence theorem, okay? And relate this integral over the surface to the volume integral over the divergence of the electric field. Okay, so just to remind you, this is the divergence theorem, and this is purely calculus, it's mathematics, okay? Any integral of the vector field E dot dA, if this is on a closed surface, okay, this should be equal to the integral of the divergence of the electric field times the tau over the same volume. Okay, so if you have any random three-dimensional shape, you can integrate the field on the surface, and that integral should be equal to the divergence of the same field inside the volume of the shape. Okay, so this is mathematics, this is calculus. We talked about this in chapter 1. I guess you are very familiar with this because you prepared for the quiz today. I'm sure you studied this as well. Okay, so now, we had this integral of E total dot dA, which we said eventually it's equal to 1 over epsilon naught over Q enclosed. Okay, so we have this one. I copy pasted from the last line here. And now, if you look at this integral on the surface should be equal to integral of the divergence of E. You know what, I want to drop this E total because should be equal to divergence of E over d tau. Correct. So these two, the right side of the integral is just divergence theorem. Okay. So on the left-hand side, what do we have? We have 1 over epsilon 0 Q enclosed. Okay. If you have continuous charge distribution inside this surface, the way we can calculate the enclosed charge density is by integrating rho r prime, okay, which is volume charge density times d tau, which is the infinitesimal volume. And this integral runs over the volume. This integral runs over the volume, the same volume. This integral runs over the surface of this shape. Okay. So this side of the equations, mathematically, these are the same. This side of the equation, this is rather trivial physics. We have 1 over epsilon times enclosed charge. We can write it in terms of 1 over epsilon integral of the charge density over the volume. Okay. And now, if you look at this, these two integrals end up being on the volume on exactly the same volume. Okay, and that's a random volume we chose. We can change it, we can make it smaller, we can make it bigger, we can make it super big or super small, doesn't matter. If we have that charge distribution, any surface and any volume we choose, we will end up this equality, where the integral of the charge distribution over volume is integral of the divergence of it over the same volume. Okay, and if this is always correct, the integrands should be the same because the limit of the integrals are the same, meaning that this, of course, combined with 1 over epsilon 0 should be equal to this. Okay, and if we write that, we get again the famous equation: divergence of electric field is 1 over epsilon rho r. Okay. And meaning that at any point in a space, if we look at the divergence of electric field, that should be equal to 1 over epsilon times the charge distribution here, the charge density. Okay. So this is technically the same Gauss law, okay? This is mathematically equivalent to what we had here. The only difference is this is the integral form and this is a differential form. Okay, so this is Gauss law, integral form of that, and this is the differential. Okay. Physically, from physics perspective, they have the same concept, the same meaning. Mathematically, again, they have the same concept, the same meaning. It's just different type, different format of presenting the same concept. This is differential way, this is integral way. Sounds good? Okay.
Professor,
Yes.
I have a question to ask.
Sure.
From your experience in using Gauss's law, which one do you end up finding they use more? The
Oh, it
integral
totally
way or the
depends.
divergence way?
Yeah, so it totally depends. A lot of times, if you have problems where you have specific symmetries, okay, one-dimensional symmetry or cylindrical symmetry, spherical symmetry, and you want to calculate electric field, we use this one. We use the integral format because we will have certain assumption on what the direction of the electric field should be, and then we can integrate how much charge. We chose surface very wisely, and we can integrate how much charge we have inside. Sometimes, especially when you are doing numerical work, you have very random charge distribution, and it's very hard to choose any big surface with a specific symmetry you can make any assumption on. So for that cases, we follow the differential format, and if you think about this will end up being a differential equation. Okay, so what we do is that we look at that differential equation, we try to solve that sometimes numerically, sometimes analytically, and then of course, considering all the boundary conditions as well. So for this course, I think we will start more using the integral format of the Gauss law. At the end, you're going to use both. Sounds good?
Thank you.
Okay. So it's 10:05. I don't have much time. I'm going to cover one more topic, and that is calculating the divergence of an electric field from a point charge, from a charge distribution. And then again coming up with the differential format of the Gauss law. And I think that's the last thing I'm going to cover today, and then we're going to stop. We will talk about quiz. Okay? So what I'm going to do next is technically a different mathematical trick to come up with this. So no new physical concept, but there's a new mathematical way. Okay? And that's so much related to all the discussion we had about the divergence of the vector field r hat by r square. Okay. So to do that, I'm going to erase everything except this one actually. Okay. So if we have volume charge density, we can rewrite this integral in terms of 1 over 4 pi epsilon 0. For dq, we can write it rho at r prime, and then divided by r square times r hat times d tau, and this is an integral over the volume that we have charge distribution. Okay. That is how we can calculate ER. Okay, and this is following directly the discussion we had last lecture. Okay, and now following this, I want to do one modification first. This integral, the limit is over the volume that we have charge distribution. I'm going to ask you does it make any difference if I change the limit to all space? Does it change?
No.
If we include everything else where we do not have charge distribution, it doesn't make any change because at those points rho r is 0. And this looks like we are adding 0 to that integral, which is going to be fine. So I'm going to change this for the sake of being able to take the divergence of the integrants here. Okay, now let's look at the divergence of E. ER. So I'm taking divergence of this. We have a constant 1 over 4 pi epsilon 0. Okay, and then we will have divergence of the divergence can go inside the integral, and that will be divergence of, we have r hat over r square, and then we have rho r prime times d tau. Okay, so technically r prime is it's covering all the source charges, and the integral is going to be on the same value. Okay, so the tau prime and rho r prime we have here. And r hat and r square are functions of both r and r prime. Okay, so we are taking the divergence with respect to non-prime coordinates, okay, with respect to r. And with respect to non-prime coordinates, the r prime here is constant and d tau prime is constant. So the only part that we really need to apply the divergence on is r hat and r square, okay, in this one. Okay. So following the discussions we had for chapter 1, the divergence of the function r hat over r square was 4 pi times three-dimensional Dirac delta function of r. Is that correct? And that is, if I want to write this separation vector distance r in terms of r and r prime, that should be 4 pi Dirac delta times r minus r prime. Okay, so this is what we have here. Okay, so this should be equal to the integral of 1 over 4 pi epsilon 0, the integral of four pi, we have rho r prime, we have delta function, delta 3, r minus r prime times d tau prime. Okay, so 4 pi and 4 pi cancel out. We have 1 over epsilon 0 outside the integral. And this is what we can simplify massively following the properties of the Dirac delta function. Dirac delta function is 0 at any point except at r equals r prime. Okay, so this integral as a whole, which is actually runs over the whole space, okay, let me write this. Okay, this integral as a whole is equal to rho at position r. The peak is happening at r equals r, and we have rho r prime here. So if we integrate over the whole space, it's 0 everywhere except right that r equals r prime. Okay, so here the integral is only rho times r. Okay, and that means the divergence of E at r, that's what we're looking at, is equal to 1 over epsilon 0 here times rho r here. Okay, so this is a different way of starting from something very general here, taking the divergence of E and showing that divergence of E is equal to 1 over epsilon 0 times charge density. Okay. Any question on this? Again, it was just a different mathematical way to reach the same conclusion. Cool. Okay. So if there's no question on this, it's 10:13. I'm gonna stop here. Okay. Give you a minute to breathe, stretch, relax, and then the quiz will be online in just 2 minutes.